All right, guys, how y'all doing? I just wanted to put together this video for you guys because what we're about to talk about is going to be a little bit skills based. So I wanted you to be able to go back and take a look at this. I'm also going to put this Google Slides presentation into Google Classroom for you so that you guys are going to have access to this as well. So what we're looking at today is kind of a follow-up to the Punnett square stuff we've been working on with determining probability. It says probability problems are used to determine the probability or characteristics or traits based upon the parent's genotypes. Remember, genotypes are the allele combinations, okay? The capital letter, lowercase letter type thing. So when we're talking about a monohybrid cross, just kind of like the ones we started off doing, one trait only, it's a pretty simple process. There's only 3 possible allele combinations. You can be homozygous dominant, which would be 2 capital letters. You can be homozygous recessive, which would be 2 lowercase letters, or you can be heterozygous, which would be 1 of each. So if one of our parents is homozygous dominant, the 2 capital letters on this particular page, it's capital B's for the dominant trait, and the other parent is homozygous recessive, which is the lowercase b's for this trait, then all of the boxes when we do the cross would create a heterozygous offspring, capital B, lowercase b. All right. If this was a dominant trait, it would the trait would be expressed every time. So since we have 4 possibilities and all 4 boxes are going to express this trait, we would say that it is 100% for our probability. Here is another example, okay? Once again, 3 possible allele combinations. We can be homozygous dominant, we can be heterozygous, or we can be homozygous recessive. If both of the parents in this case are heterozygous, so that's capital A, lowercase a, then you'll get the following possibilities when you do the cross. So when we do our cross, remember our A from this parent on top is going to drop down. The lowercase a will drop down. This A right here will move across, and this lowercase a right here will move across. So when we look in the boxes, we have 1 out of 4 boxes is homozygous dominant, capital A, capital A. That's 25%. 2 of the boxes have a capital A and a lowercase a to make it heterozygous at 50%, 2 of 4. And then the last box is lowercase a, homozygous recessive, 25%, 1 out of 4. Okay, so it's really easy to determine the probability of offspring in a monohybrid cross. But what if we're looking for a specific offspring genotype from a much more complicated cross? It becomes very difficult and time-consuming to have to work a huge Punnett square to determine probability. This square that you see on your screen right here is a trihybrid cross. It deals with 3 characteristics. In this case, it's A, B, and C. And you can see that it requires 64 boxes to do this cross. Then once you got your, once you got your 64 boxes, you would have to go through and you would have to count which ones are what you're looking for. That's what these color codes are on here. So luckily there's a shortcut. There's an easier way to determine the probability to where we don't have to go in and we don't have to do all of those crosses. So let's just start off right here. It says, let's say the parents have the following genotypes. The mom is heterozygous for A, heterozygous for B, homozygous recessive for C. Dad is homozygous dominant for A, heterozygous for B, homozygous dominant for C. And we're looking for an offspring that is AA, homozygous dominant, capital B, lowercase b, heterozygous, capital C, lowercase c, heterozygous. So if we view each trait as an individual monohybrid cross, and remember that a monohybrid cross only has 4 possibilities or 4 possible outcomes, then it's going to become a lot more simple than doing one of those great big 64 box Punnett squares. So think about it like this. Each parent has 2 alleles for each trait, but can only contribute 1 to the offspring. Every offspring, every child gets 1 from the father from the sperm and 1 from the mother in the egg, okay, to give it the 2. So that limits our possibilities. In this first example, parent 1 gives, you can see parent 1 is heterozygous, so is parent 2. Parent 1 is going to give this homozygous dominant A, and parent 2 will give the homozygous dominant A. So we've got this arrow pathway to make that happen. Okay. Here, parent 1 is going to give the same allele. Parent 2 is going to give the other allele, the recessive. So we can follow this arrowed pathway. Our third possibility is parent 1 gives the lowercase, the recessive allele. Parent 2 gives the dominant allele, following this pathway. And our last possibility is parent 1 gives the recessive, and going straight down, parent 2 also gives the recessive. So that's how we get all of these possibilities in our Punnett square like we've been doing. So if we know our genotypes of the parents and we know the genotypes of the offspring that we're looking for, we can count the arrows and do a little bit of simple math, and it's going to tell us the probability or the percentage of that particular offspring's genotype. So let's look back at our original scenario from a few slides ago. Mom, heterozygous for A and for B, homozygous recessive for C. Dad, homozygous for dominant for A, heterozygous for B, homozygous dominant for C, and we're looking for an offspring that is homozygous dominant for A, heterozygous for B, and also for C. So the first thing that we want to do is we just want to set this up visually to where it's easy to follow along. So we're going to put one parent on top, one parent on bottom. Doesn't matter which one, mom or dad, parent 1, parent 2, however you want to do it. Doesn't matter. Just line them up like you see on the screen. And then the offspring that we're looking for will go on the bottom. Okay. So the next thing we want to do is we want to put in the arrows that will create the desired offspring. We want to figure out all the possible allele combinations that will work. So when we take a look at our offspring, we're looking for capital A, capital A. There's two ways that can happen. We can get the capital A from mom and this bottom one right below it from dad, or we can get that same capital A from mom, that same dominant allele, and go diagonally and get the other allele from dad. One of those two pathways is the only way it'll work. For the B's, we want capital B, lowercase b. The only way that will work is to get the capital B from mom and then go diagonally and get the lowercase b from dad, or we can get the capital B from dad and the lowercase b from mom. So there's two possibilities there. For the C allele, we want it to be heterozygous, a capital and a lowercase. There's actually 4 ways that this can happen with this parent combination. We can get this left dominant allele from dad and the left recessive allele from mom. We can get the same allele from dad and go across and get the other recessive allele from mom. We can get the right dominant allele from dad down here on the bottom right and the top left from mom, or the same allele from dad and get the top right allele from mom. Any one of these pathways will get us to that heterozygous combination we're looking for. Step 3, we're going to count the arrows from each section. In the A section, we had 2 possible pathways, 2 arrows. Same thing for B. Here we had 4 possible pathways to make that happen. So we got a 4 here. Step 4. Set up a fraction with the number of arrows as the numerator, the top number, and 4 as the denominator, because we only have 4 possible choices. And then we want to reduce, we want to reduce that fraction if we can. So for the A's, we had 2 arrows. We're going to put it over 4. 2 over 4 is the same thing as 1/2 when you reduce that. Same thing for the B allele. We had 2 arrows over 4 for 1/2. The C allele, we had 4 arrows. 4 divided by 4 is 1. Okay? And then step 5, we're going to multiply. 1/2 times 1/2 times 1 equals 1/4, or a 25% probability. 1 out of 4 is 25%. So if we have this genotype for parents, we have a 25% chance that the offspring will be this genotype that is in green right here. Okay? Let's look at another example, putting this all together. Here we see mom is heterozygous all the way across. Dad is heterozygous all the way across. And we are looking for a heterozygous offspring. Okay? So we've got them on top of each other. Here's our possibilities. Mom, capital A and this lowercase a, or dad, capital A, and mom's lowercase a. That's the only two possible ways to get the offspring to have heterozygous, capital and lowercase. And then that's the same for B and the same for C. So we have 2 arrows for each allele combination. For our fractions, each one of these will be 2/4, which is 1/2. So if we multiply 1/2 times 1/2 times 1/2, we get 1/8. 1 divided by 8 is 12.5% probability. A heterozygous mom and a heterozygous dad have a 12.5% chance of producing a heterozygous child. Okay? So last thing on this, here's our proof. This is that same Punnett square from earlier, 64 squares in here, all right? If we're looking for the heterozygous offspring, the trihybrid cross shows 8 boxes out of 64 that are heterozygous. They run diagonally from the bottom left to the top right. If we look right down here in the bottom left box and we go diagonally all the way across it in this lime green color, those 8 boxes in that color are the boxes that are heterozygous for all 3 of those traits. 8 boxes out of 64. 8 divided by 64 is 12.5%. So instead of creating this giant trihybrid cross and then going through and finding what we're looking for and counting the boxes, we can skip all that by doing this process right here. Okay? So this is what your assignment's going to be about on probability. I encourage you to take a look at this video again. If you have any issues, don't hesitate to ask or send me an email. Good luck with this, guys. Have a great day.